Hello, everybody. Testing, 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 1, 2. Thank you for joining us. This is our first attempt at the YouTube live stream, so I want to make sure that we get the audio set. Hello, everybody. Testing, 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 1, 2. Seems like it's coming through well. Get started here in just a second. Hey, Kelly Jo. Great to see you on here. So it looks like we've got a few folks who've joined in so far, so we will get started, and this will get recorded as well for anybody who wants to rewatch it afterwards, or for anyone that you would like to share this with, or for anybody tuning in after the live. Welcome. So good morning and good afternoon to everybody, depending on where you're checking in from today. It's just noon here on the East Coast. And I really appreciate everyone taking time out of their schedule to join our presentation on model risk management today. As some background on myself, my name is Michael Thomas. For those who haven't met me, I'm the Chief Data Scientist at Ketchbrook Analytics, which is a data science consulting firm based out of the Hartford, Connecticut area over here in the USA. I know we have some international viewers as well today. And our motto is that we develop data science solutions designed for you specifically. And we take all the words in that motto very, very seriously. We want to make sure that whatever we build is a solution to your problem and not just a Band-Aid, and that it's designed with your users specifically in mind. So the topic here today is on model risk management. And you might be wondering, necessarily why we care about model risk management, or MRM for short. There's a lot of focus on building models and using the latest and greatest AI and machine learning techniques to build highly accurate models. And many consultants, including us, we can help you do that. But we feel that there's also maybe not enough focus, however, on everything that comes after that. So questions like, what's the right way to deploy this model based on the technology framework that our company uses? What are the metrics that I should be monitoring to make sure the model continues to stay accurate in the future? How do I ensure that the model is locked down and secure from an internal controls standpoint? And how do I make sure that the model is fair and unbiased? And we're going to talk about all those things within the context of internal controls risk, technical risk, legal risk, and what we're going to call model risk as well. So we'll start with internal controls actually, and we'll talk about the power of version control and how if your organization is starting to build models, but they are not using version control, that they should be doing so, and that using version control solves a lot of those issues that you might face from an internal controls perspective as you begin to build models within your organization. So the idea here around version controls really focuses on a code-first approach versus spreadsheets. Over on the left side of the screen, we have a picture of some code, and over on the right side of the screen, we have a picture of an Excel workbook. And maybe you have built in the past some models within Excel workbooks, and maybe, and hopefully, you are starting to potentially migrate to a code-first approach as opposed to spreadsheets. And the large benefit that a code-first approach gives is that code is written from left to right. and then top to bottom. The same way that you would read a book is the way that someone else can interpret the code that you write and the way that a computer interprets the code that you write. So it also serves as sort of a recipe of steps that you're going to make along the way. You start at the first line, then your next step is the second line, and so on and so forth until you get to the end of your script containing your code. As opposed to an Excel workbook where maybe I have one cell that relates to another cell over here, and then kind of the next step was a cell way down here that relates to a cell up there. And then, lastly, I have a cell all the way over in the top right that relates to a cell all the way over in the bottom left. And there's no recipe for someone else to follow along with, how you got from point A to point B as you developed your quote unquote model in an Excel spreadsheet. So it also makes that very difficult to version control and to provide internal controls around for anybody who has tried in the past to put a set of controls around an Excel spreadsheet. I'm sure you've come into understanding that it's a very difficult thing to do. The other real benefit is that code is just a text file. So it provides you with this other gigantic over spreadsheets in that code is what we call differenceable, meaning that we can easily track the changes made to a piece of code over time. As opposed to maybe on the right side of the screen, if you're familiar with building models in Excel, you might have a model version 1 final, a model version 2 final 2.xlsx, and then something like I swear this is seriously the last version, model version 2.xlsx, and that's no way to version control your model as it progresses over time. So if we look kind of at that left picture and we blow that up on our screen, we can take a look at an example of where I made a change to the code in one file on the left, and when I did so, we were able to use version control to see exactly what changed. And the version control software actually highlights for us at the bottom, in the bottom two lines, the two places where our code changed. We changed the number 1.98 to 6.58. That's highlighted in red on the left and then green on the right at the very bottom. We changed the number 4 to AAA, and we changed the number 6 to an A. And this is incredibly powerful because this software that we have for version controlling things actually points out these exact changes for us. And we don't have anything like this on the workbook and spreadsheet side of the equation. So it not only provides us with great internal controls where we can track these changes over time, but it provides us with an incredible efficiency gain as well. When, as a reviewer, you have the power to see exactly what changed. You don't need to re-review the entire code or re-review every cell in an entire spreadsheet every time your data scientist or data analyst go to make a change to your model or a change to the business logic. You only have to focus on reviewing what changed between their updates and what's currently in production. And version control explicitly shows us that. So what this looks like in practice for more of the visual folks on the call is, we have a version of our model, say version 1.0, that's been blessed, and it's running in production, and our organization is using it to make decisions, and maybe our model is even deployed somewhere where its predictions are actually automating the decision process, something like maybe a Rocket Mortgage, where it's actually, we have a model behind our website where folks are going in, interacting with it, and it's automating the decision process. So we have this version 1.0 that's running in production so far, and it's working well. But periodically, we'll want to get new data that we'll use to retrain our model. We want to keep our model up to date and fresh with the changing, macro environment out there and the changing data that applies to our particular model. So we send our data analysts to run an experimental analysis that shows that maybe adding some new variable that we weren't using in our model before will increase its predictive power. So we want to do this retraining or experimentation on an identical copy the code that's running in production currently, so we can make sure any changes we make have fidelity to the current environment without breaking or interfering with the production environment while we experiment and make sure that these changes are stable. So once our data analyst or data scientist, goes out, does their work, says, hey, I've made these changes, I feel really confident about them, I want to submit these changes to be pushed into production and get used in the new version of our model. We need to have some controls around that in place before those changes actually get made. And a few of those are, the first stop should be automated testing. So we should put this particular control in place first to ensure that our changes don't break any of our underlying assumptions about the model. So I can show an example, of one such test that we've written for a credit decisioning model, sort of like a Rocket Mortgage that makes decisions automatically about whether or not a particular borrower is expected to repay their payment. So I can bring up an example of some R script that we have here, and behind it is two data sets. So we have a first data set called Model Data 2021, June 30th. So this is what we originally trained version 1 of our model on. And then lower, we have another CSV with the new data on it. So we want to make sure that when we bring in this new data from our latest quarter, we want to make sure that we don't have any industries that didn't exist when we originally trained our model. So we're trying to say that we train an original model that understands how to make decisions on particular industries, but if our business started lending to a brand new industry that our model has never seen before, we want to explicitly point that out before anything makes it into production. So we can run a test, and both Python and R have great frameworks for running tests, and we can actually test that there are no new factor levels exist in our variable industry that our model is using. And we want to expect that these two things are identical, the old industries and the new industries. So we can execute this test right within RStudio, or you can use Python's framework as well. And it's going to tell us that it found a new industry, that there's a fruit industry that did not exist in our original data set. We had 3 industries originally, and now we have 4. There's this new industry that it found. So this is an assumption that we had baked into our original model, and we wrote a test to protect ourselves from breaking that assumption. And you should be using tests in any modeling or analytics work that you do, because pretty much any statistical analysis at all is going to have to make some assumptions about the underlying data behind that. And writing these tests can protect you from breaking those assumptions. So let's hop back into the slideshow. So let's say that we passed all of our tests and that the new changes that we made still satisfy our assumptions. So platforms like GitHub and GitLab and Bitbucket have the ability to not only run these automated tests themselves and stop code from getting to production if a test fails, but they also prohibit changes to be pushed to production until they have a set number of review sign-offs or until they're signed off by a specific person. So in this example, if the new code changes past the tests that we've written, the code must then pass this other hurdle, and that's get signed off on by a peer reviewer, which could be another data analyst or data scientist that we have. If the code passes testing and peer review, then it should probably hit somebody like the analytics manager or whoever the model owner is. And this person should perform that final sign-off before the updates actually hit production. And if they do hit production, then we can tag our new model and we can use version control to explicitly state, hey, everything historically to the left of these changes that were made is version 1.0, and everything to the right of these changes that were made is version 2.0. So a lot of these topics don't get discussed, maybe in your traditional statistics or data science curriculum, because the focus again is so much on building the best models possible. But when we apply these models in practice at an organization, we need to make sure that we are managing the risk around these models, which is exactly what we're talking about today. And we don't have to reinvent the wheel. Model risk management is a fairly new term, but the tools and techniques that we use to manage model risk are not necessarily new. And most of them come from the software engineering world, where there's already this set of great best practices that we can use and adopt for our models that we develop. For instance, if we look at a timeline in history, so there's been incredible advancements in software development best practices for the last 40 or 50 years. And data science as a term has only been around since the early 2000s. So we shouldn't assume that as data scientists, we have all of the tools ourselves, or we understand everything that there is to know about managing our models just within this short time frame. We need to understand that there's this whole other set of best practices that's already in place out there that we can borrow from and we can gain a lot from. So I want to talk about the next risk is technical risk, and specifically avoiding technical debt. And if you've never heard the term technical debt before, it's around putting things into place from a technology perspective that only one person understands. And when that one person walks out the door, if it's not well documented or not well understood what it is that they built, it becomes very difficult for anybody else to pick that up or even to collaborate with them on it if they haven't walked out the door yet. And there is a set of standards for building software tools and building predictive models to ensure that we're not leaving behind technical debt, that we can use these frameworks that are agnostic and that others coming into our organization should know and understand because they are best practices. And I want to first start off with one definition that I'm going to use throughout the remainder of this talk, and that's something called a repository. And a repository not only contains all of your files and code around your model, but it also contains all of the historical changes that have ever been made to those files and code. So you can think of it like this single folder that contains files and other subfolders, and the current state of that repository should be a one-to-one map to the folder on your desktop that it's related to. And right now we're moving on to some more tangible things and less theoretical things that you should include alongside your models to ensure that you are managing their risk appropriately. So what are the attributes of a healthy repository? What should go in this kind of big folder that contains everything related to your model? First is the license file, and this relates to legal risk. It defines the ownership of your code in the event that your code gets into the hands of someone outside of your organization. Perhaps you're even building some sort of a software tool that you want to share with others publicly. But most of the time, you're probably building software or building models that is proprietary to your organization. So if someone does get a hold of this code base or this repository, you want to make sure that you have the ability to take legal action against them if they use that for any particular benefit. And this is very important in getting your legal team up to speed as you start to develop models on what needs to be incorporated from a legal perspective. So again, most likely this will be proprietary. So if you have full ownership, you might just have a file, and this is just a simple text file that you want to have included alongside your code that states something like this. It has copyright, and it probably has 1, 2, 3, 4, 10 different sections of legalese that your legal team has put together to ensure that everything in here is proprietary and is owned by you, and that's explicitly written. So maybe you're even developing tools that you're licensing to someone else, and they're paying you for your model or for a particular app that you've built. Your legal department would want to articulate that in this license file as well. There are also the potential for you to kind of co-own the models or the work that you've done. So you might want to use portions of the work that you've done for the public benefit. So we can take a look at, T-Mobile here. They have developed a great repository that allows folks to use parts of the code in this repository while allowing, while ensuring that they cannot use other parts of this repository. So we can even click on this link. It'll take us to their license file in this repository, and it states the permissions here. This is the explicit text here of this license file, and it shows up really nicely here on GitHub what the permissions are. So you can use this to distribute. You can use this to even create a patent or for private commercial use. But what you can't do is you can't use T-Mobile's likeness for trademark purposes to sell this particular software as you've adopted it, under the guise that you're T-Mobile. They're also not providing, any liabilities or warranties that the code that they've put together here that they're allowing the public to use, is perfect. So you can't sue them if you use this for your own or within your own organization and you find a bug or an issue in it. So there's a lot of different options from a legal perspective on how you might want to license the code and the models that you're writing, and it's important to understand the different options that you have and to put in place the one that makes the most sense for the project that you're working on. So the next file out of these 4 files that are very important to have is called the description file. And this states the dependencies that are necessary to run the code. And this is really, again, about managing the risk of technical debt. And I can show you quickly what a particular a description file might look like. Let's see if we have one here. So it contains the authors who have worked on this particular piece of code, a title, and then what it's going to do is it's going to state your dependencies. So in order to run this code, we need a version of R installed that's greater than version R 3.1. We need these particular packages as well on top of that. And this also states where the license is and what types of license is there, and a couple different other pieces of information that are very important for anyone coming into your organization to understand how to recreate the work that was performed. And again, this is an agnostic file that others coming in or other reviewers should understand how to read and interpret. And it's very important that you incorporate this description file within your code as well. So when we talk about the dependencies in that description file, we're talking about really ensuring that what we put together is reproducible and preventing the risk of not being able to reproduce our model results. And there's 3 people that we want to be able to perfectly reproduce our results, or else we'll have major issues. One is any validators that we're hiring or are coming in to validate the model that we've created and ensure that they can reproduce our results. Second is a regulator that's coming in to audit us and make sure that they can reproduce the work that we did so that they can sign off on that third-party audit that says that, okay, the model that you've created is good and dandy. And then the last person that it's very important to satisfy is ourselves or our team in 6 months or a year from now to make sure that we can reproduce our work. I think anybody who's written code before has run into situations where they've tried to recreate their results a month or 6 months or a year later and have been unable to do so. So you have to understand that there's 3 components here to ensuring that you can exactly reproduce the work that was done. That's the operating system, that's the software dependencies like R and Python, and that's the specific code on top of that. So those 3 are the ingredients for that recipe of reproducibility. It's not good enough to say that we built this model in R and here are our scripts. We need to explicitly define that we installed R version 4.0 on Windows and dplyr and ggplot versions 1.5. And the person trying to reproduce your results should really be able to run one single script to get your results, not having to run script 01 first and then script 02. So we'll talk about specific tools for ensuring reproducibility. You also might want to include a visual diagram within your repository that shows exactly how your model works. So you're probably starting out grabbing your data from some data warehouse, doing some data manipulation or ETL, maybe creating some files out of that, some static flat files that you're going to use for model training purposes, and you want to isolate those files for historical purposes. You're going to get some reporting about your model's accuracy after you trained it, and you want to memorialize that as well. And then you probably have some configuration files in your version-controlled repository that are used to actually configure getting this out into production and deploying our model that we have. And then you want to show how users would interact with that model, and that the decisions that get made in tandem with the user's inputs and the model's response get written back into our data warehouse so that we can track our model's accuracy over time. There's a couple different model deployment options, APIs like Amazon's recommendation engine that you don't even understand is going on behind the scenes. As soon as you log on, it's grabbing some information about you and running that through a model and showing you particular products based upon that information. There's a batch process where maybe on a nightly basis, the CEO of your company wants a forecast of the next day's sales. Or there's also, ad hoc simulations within a web application where a user can go and tweak some model parameters and maybe run 10 simulations or 1,000 simulations to understand the probability distribution of potential outcomes and likelihoods within a clinical trial setting, for example. So a few different options that you have there, and you want to think long and hard about how you're going to deploy these things. So lastly is a README file that walks folks through the purpose of the code that you are writing. A good README file might have some text as well as some pictures and visuals and images. And we can look at our nice README file here in this particular repository, which we built an R package called migrate, and we state the purpose at the beginning of it, the goal of this package. We talk about the methodology that we use, how to install it, and even some examples of running the code. So the last thing that I want to touch on is model monitoring. And we need to do this mostly through data visualization and dashboarding because we want to monitor the model's accuracy over time, and we also want to model bias and ethical implications of our model. So maybe in this particular chart, we have one line, the blue line, that's just looking at the overall rate of acceptance in our credit model that's automating lending decisions. And then we have a red line that shows the rate of acceptance of a particular protected class. And this is something that we want to follow over time. This must be done for any protected group or class. And if you do see a significant difference on like a time series chart like this, you probably want to go to the next step to perform a hypothesis test to see if it's just a function of randomness occurring, right? Or if it's actually a statistically significant issue embedded in our model. We've seen folks who say, hey, we don't use race in our model, but they're using zip code or a variable like that, which is potentially very much a proxy for race. Or even age, but using zip code if the zip code's a college town, which can be a proxy for age as well, right? So you have to think long and hard about the potential bias that you might be baking into these models with the data that you've historically collected, which may have some bias encoded in it. We have at Ketchbrook Analytics developed some tools like our model manager application. We understand that every model is different, and there are different assumptions that go into it, different accuracy metrics that are relevant from one model to the other. So we like to build 80% of the app and then work with our clients to build the last 20% of the app tailored to their specific use case. And if I were someone evaluating MRM solutions, I'd be very cautious of any vendor trying to sell me a one-size-fits-all MRM solution, just because models are specific to your particular business and then even more specific to the particular use case that you're trying to solve. So an MRM application might look something like this, where we have, for example, a dashboard that shows us our last refresh date of our model, the current model version. We can look at the approval rates if we're building, a credit model that's approving or denying somebody applying over time. So in February of 2021, we were using this model to approve 86.8% of the loans that passed through it, but then down in May, it was only 78.6% of the loans that passed through it. And you might want to have some aggregate statistics up here with a default rate of approvals, so that you're tracking over time to ensure that your model continues to be accurate. If you're starting to see that the approvals that your model made over time, that default rate is actually getting worse, so model decisions that you were made, these customers are actually not paying back their loans, that's absolutely something that you're going to need to track. You might want to have a screen that captures the accuracy statistics and potential model diagnostics for each model version that you've had in production in the past. So we can take a look at our specificity versus sensitivity in a chart like this, where we can see, hey, our model got it right on the good loans, 2,172 out of 3,800 total observations, and it got the bads right 1,493 times, but in cases where the actual case was good and our model thought it was a bad loan, it got those wrong 39 times. And in cases, which is probably the worst case scenario, where the loan was actually a bad loan, but our model thought it was a good loan, that happened 96 times out of the total 3,800. So these are all sorts of different metrics that are specific right to the model that we've put in place, which is a classification good, bad model, but might vary depending on if you have a forecasting model in place or something else like that. So we have all sorts of different screens, and if anybody would like to follow up with us, please shoot us an email to talk about our Model Manager app and how it might be able to fit within your organization. And I know we're just about at time here, so I do want to thank everybody for their time. I know we ranged, heavily from high-level strategies to some pretty technical tool demonstrations. But if you're an organization that has phenomenal domain experts and quantitative skills, who are writing code, you have data analysts doing great analysis, you want to make sure that their hard work is standing on a solid foundation and not a pile of sand. And this means surrounding their work with strong model management and software development practices. You see the value of turning their domain expertise into valuable tools, predictive models that are running in production, interactive web applications, but maybe you don't currently have the resources with this software expertise because those resources are expensive and hard to come by, and it's not necessarily fair to your quantitative staff for them to also be full-blown software engineers. And this is really where the power of collaborating with us on a project comes in handy. We work side by side to turn your team's domain expertise into stable, robust software that tangibly moves your organization forward. This work is what we call the final 10% hurdle of the project, but it makes all the difference between determining success and failure in an analytics initiative. So again, thank you for your time. If you do have any questions, we would really, really love to hear from you and reach out. We will absolutely send this recording link out to everybody that attended and registered, but you can reach us through LinkedIn or probably best through that email at the top, info@ketchbrookanalytics.com. Thank you so much again for your time, and we look forward to hearing from you soon.